Welcome, folks. This structure is taken from the S-shaped growth structure that I've gone over in a previous video. And you can see that it generates the S-shaped growth. This is a comparative graph of deer on the bottom, and it's the deer versus the capacity in that top graph. And right now, the way it's working is the deer and the carrying capacity in the ratio of deer to carrying capacity. I'm simply dividing deer by the carrying capacity. This has been normalized, there's dimensionless, and that's going into this effect. And if I double click on the effect, right now we have it as 1 minus the ratio. So you can imagine as this ratio grows from 0 to 1, this fraction would be getting smaller and smaller and smaller. And then if I go to net bursts, I'm just multiplying by that number that's getting smaller and smaller, so I'm shutting down the net bursts, which then goes into equilibrium. When this equals 1, 1 minus 1 is 0. The net burst is 0 unchanging, and therefore the deer are going to be unchanging. What I'd like to do is make this a nonlinear. I'm going to do this in a couple of steps. So I'm going to get rid of the 1 minus and just say it's going to be equal to the ratio. I'll double click on this again, and now I'm going to go down, and here the second icon on the bottom says graphical function. I'm going to click on this graphical function, and I'm going to click on this graphical. And I know this ratio should go from 0 to 1, and the ratio is here on the x-axis, so I'm going to make that 0 to 1. And I want it to grow at the most. If it's very, very low, I want it to grow at the baseline birth rate. So on my y-axis, that will go from 1 to 0. And I'm going to make it linear to start out with, and I have these different graphs that I could select that are built in. And I will just select this, and this is the same as it was before. The 1 minus the ratio is what this is equal to. This is linear. For every 10% increase in that ratio, I have a 10% decline in the output, or the effect of the carrying capacity ratio on bursts will decline by 10%. So I'm going to simulate, and what I expect in this deer graph here, that's a comparative graph, that the next simulation will be identical to the first. And you can see that it is identical. So now I'm going to go into the effect, and this should be nonlinear. And I've got different things that I can select from. And basically nonlinear means that it's not going to be proportional as this increases from 0 to 1 or declines from 0 to 1, that the changes are not going to be proportional is what nonlinear actually means. And so what I'm going to do is I'm going to start out by making it slightly curved. And I could go down to this and make it more or less curved. And I'll go with this slightly curved. And what this is saying is initially, when the population starts to grow, there's less effect than there was in the linear, and there's less effect. But when we get to 1, that net growth should be 0, or the net burst should be 0. So I'd be multiplying by 0 in this case. So let's click on this, and I'm going to run this again, and I'm anticipating that I would see a difference in this growth of deer here. And you can see that they actually grow faster, and they reach an equilibrium, and they stay there. And if I look at this, they're growing faster because this is greater than it would have been under the linear condition. So I'm allowing that growth to occur more, and then it's going down. So I'm going to change this even more. And I can go in and click on the graph again, and it opens this curvature here. And let me just crank it all the way over. And what this is saying is that if I have 10%, the birth rate is going to be the same. If I'm up to around 20, 30%, the birth rate is almost the same. I get up to 50%, and then the birth rate just starts to change, just a very small amount. And then as I get up to 80%, I'm starting to see a 10% decline in the birth rate, and then as I get to 1, the birth rate is really falling off. So what I anticipate that it could grow even faster is what's occurring. The effect isn't kicking in until later, until the deer is approaching that carrying capacity. Again, the definition of a nonlinear function. And you can see it goes up to the green line here and cuts over. So I'm making this, so I could do this one more time. And I'm telling stories when I'm drawing these graphs. Let's make it just so that, and it's got to be a negative slope. It's going from 0 to 1, and it's going to be declining. So let's make it more S-shaped. That there's going to be in the center, when I'm going from about 30 to 70%, there's a steep decline in the birth rate as the area is becoming crowded and there's less food, is sort of the argument. And then it's leveling off at 0. When it's 1, it's just impossible for them to actually grow. They've reached that carrying capacity. And I will simulate this one more time, and you can see that it's growing very slowly now as it approaches. And what's happened is I've started to slide down this graph, or this graphical function, so that it's at 60%. I've been reducing. It says the output there is approximately 0.26, so that I've reduced it by about 75%, the birth rate, because of crowding in this case, is what we're arguing. And it slows down the approach to the carrying capacity. And that's all a nonlinear or a graphical function is. Again, we're telling a story about this, but I just wanted to get you how to build these in Stella. That's it for now. I'll see you folks.